Sa slides, paano ba sa slides yun? Teka lang. Ito, play, present.
Ayan, sa slide, yeah.
Thank you for being patient for this presentation. So let's start. I have the topic, abstract data types, implementations, abstract functions, representation invariants, and notions of equality for the subject, advanced system design and implementation. So good afternoon, classmates. I am Grace Ching to present this report. And as an overview, of course, we'll be discussing what is abstract data types and its corresponding implementations, abstract functions, and representation invariants plus the notions of equality. So first, play. Ayan. Oops. Medyo naglalag pala. Ano ba magbalik?
Araw daw lang. Araw.
Okay. Naka-remote kasi.
Naka-remote. Oh, hindi ko rin alam yan. Pang mayaman yan.
Ayan, nag-move na. Ayan, there you go. First, let us define what is abstract data types. If you look into...
Hindi siya naka-share.
Hindi. Ano ba?
Gracial, what if i-send mo na lang tapos iba na lang ang mag-share?
Sige. Much better. Thank you very much for that. Nag-send ako nung copy sa ating Facebook.
Oo, tapos i-share na lang dito.
Alright.
Oo.
But I'll try it again. Medyo nakuha ko na yung function. Nakakahiya kasi masisira yung concentration yung makinig. Wait lang. I'll try it again. Then, let's settle dun sa... Ayan, can you see?
Yes.
Ayan, na-navigate ko na ng maayos.
Yan, okay na.
Yeah. Thank you. So for us to continue, abstract data types, we should define the abstract data types. First, if we were to look at a program that is actually large enough to require a full team of programmers to implement it, we all know you would probably not be surprised to find that it would not be organized as a single large monolithic unit, but instead as a large number of cooperating functions, right? We are familiar on how to design and write functions in, I don't know, in C++ or other object programming language like Java. We will be discussing some samples regarding C++ and Java. I hope you are all familiar with that. And then, however, come as a bit of a surprise if you have not worked much with the programs that size is that even these functions will be further organized into higher level structure, correct? First, let us define abstract data types, or also known as ADT. Its definition is an ADT is a programmer-defined type with a set of data values called the domain, a collection of allowable operations on those values which defines the design. As for its implementation, it consists of a concrete representation of the abstract data in terms of existing data types and off-the-shelf ADT operations. The implementation may include program code or even hardware that implements the allowable operations. Characteristics of an ADT, which should be useful, of course, reasonably represent the real world and complete design of the project. It must be sufficiently abstract. The abstraction barrier or information hiding issues we are currently encountering in real life application is when the creator of the ADT is guaranteed that the user can access the encapsulated data only through the allowable operations. Another is when the user is guaranteed the ability to use the ADT without having to know how it is implemented. So to proceed, should be aware on what uh naku, hindi nasama yung title, but it should contain what does a good program define. Siyempre, it works well as specified based on the requirement. And then number two, it is easy to understand and modify. And then third, it is reasonably efficient. So one way to help achieve the two, item two, which helps with the item one, is to use abstract data types or ADTs. The idea of the ADT is to separate the notions of specification or whatever kind of thing we're working with, what operations can be performed on it, and implementation on how the thing and its operations are actually implemented, right? The benefits of using abstract data types is it gets the code easier to understand, such as it is easier to see high-level steps being performed, not obscured by low-level code. And then implementations of ADTs can be changed, such as for efficiency, without requiring changes to the program that uses the ADTs. ADTs can be reused in future programs. So that's where we get its efficiency. Fortunately for us, object-oriented programming languages such as Java and we have mentioned C++ earlier, make it easy for programmers to use ADTs. Each ADT corresponds to a class or Java interface, more on this later. And the operations on the ADT are the class or interface's public methods. The user or client of the ADT only needs to know about the method's interfaces, the names of the methods, the types of the parameters, what the methods do, and what, if any, values they return, not the actual implementation or how the methods are implemented, the private data members, private methods, and etc. Abstract data types have two parts in its ADT. The public or external part, which consists of the conceptual picture of the user's view of what the object looks like, how the structure is organized, the conceptual operations, what the user can do to the ADT. The private of internal part consists of the representation of how the structure is actually stored. The implementation of the operations is the actual code. In general, there are many possible operations that could be defined for each ADT. However, they often fall into these categories. Uh, could be it could be on the initialization, the adding of data, the accessing of data, the removing of data. Where in this class, we will in this defined categories, we will further look into this in the succeeding slides. Uh, uh, okay. And then let me change the slide. And this diagram, the abstract data type ADT is a type of or class of for objects whose behavior is defined by a set of value and a set of operations. The definition of ADT only mentions what operations are to be performed, but not how these operations will be implemented. It does not specify how data will be organized in memory and what algorithms will be used for implementing the operations. It is called abstract because it gives an implementation independent view. The process of providing only the essentials and hiding the details is also known as abstraction. The user of data type does not need to know, look into that, how that data type is implemented. For example, we have been using primitive values like int, float, char, data types only with the knowledge that this data type can operate and be performed on without any idea of how they are implemented. So a user only needs to know what a data type can do, but not how it will be implemented. Think of ADT as a black box, which hides the inner structure and design of the data type. And then we can understand it better if we'll define the three ADTs, namely the list ADT, stack ADT, and queue ADT. So this is the what do you call, what you're seeing right now is a diagram for the list ADT. The data is generally stored in key sequence in a list which has a head structure consisting of count, pointers, and address of compare function needed to compare the data in the list. The data node contains the pointer to a data structure and the self-referential pointer which points to the next node in the list. A list contains elements of the same type arranged sequential. Oops. Sec- oh no. Nag-lag out. For a while I'm having technical issues dun sa aking Google. But are you still seeing my screen,
Yes,
guys?
ma'am. Yes, ma'am.
Sige po. Sandali lang po. So where did we stop? Dun sa ating diagram ng list.
Gracia,
Okay,
yung nakikita namin sa screen, abstract data types, ADT.
abstract data
Yes.
types, and that's a diagram with green squares
Oo,
with the
list
list,
and
count,
node.
compare. Ayan. That's correct. That's the diagram for the list ADT. Yeah, let me continue. So in this diagram, the data is generally stored in key sequence in a list which has a head structure consisting of count, pointers, address. I hope you can see. Uh, Address of compare function needed to compare the data in the list. The node contains of the pointer to a data structure and the self-referential pointer which points to the next node on the list. A list contains elements of the same type arranged in sequential order and following operations can be performed on the list. A sample of this syntax being used in here is in Java we use the get, insert, remove add, replace, size, is empty. So a get return an element from the list at any given position. The insert inserts an element, of course, at any position on the list. Remove removes the first occurrence of any element from a non-empty list, and so on. And then the next type of ADT is the stack ADT. I hope my screen is moving as well. Yan. In stack ADT implementation, instead of the data being stored in each node, the pointer to data is stored. The program allocates memory for the data and address is passed to the stack ADT. The head node and the data nodes are encapsulated in the ADT. The calling function can only see the pointer to the stack. The stack head structure also contains a pointer at the top of the count. Can you see in the diagram? Of a number entries currently in stack. A stack contains elements of the same type arranged in sequential order. All operations take place in a single end that is top of the stack, and following operations can be performed. So in this, we can use the syntax like push, pop, pick, size, is empty, full. So in push, we can insert an element at one end of the stack called top, and then pop. We can remove the return statement at the top of the stack if it's not empty. Well, on peak, we can return the element at the top of the stack without removing it if the stack is not empty. So another type of data type is the the QADT. The Q abstract data type follows the basic design of the stack abstract data type. Each node contains a void pointer to the data and the link pointer to the next element in the queue. The program's responsibility is to allocate memory for storing the data. Let me check if you're seeing the slide right. Okay. A queue contains elements of the same type arranged in sequential order. Operations take place at both ends. Insertion is done at the end and deletion is done at the front. Following operations can be performed. Examples are NQ, the queue, peak, again, peak can be used in here too. Size, and then is empty and is full. So in NQ, it inserts an element at the end of the queue. The queue removes the return of the first element of the queue if the queue is not empty. And given with those definitions, we can clearly see that the definitions do not specify how these ADTs will be represented and how the operations will be carried out. There can be different ways to implement an ADT. For example, the list ADT can be implemented using arrays or singly linked list or doubly linked list. But similarly, ADT and QADT can be implemented using arrays or linked list. All right. And then, as an example, um, we can simply say thermostat as an ADT. Its domain and its operation. So, for example, the domains are the temperature setting between 50 and 85 degrees Fahrenheit, correct? And there is an on and off switch setting for the cooling unit for the thermostat, and on and off switch for setting for the heating unit. The domain values often represent the private variables and structures that must be implemented. So in this case, we can use the operations as a turn up. So we can do the functions like to raise the setting by 1 degree, turn down, like to lower the setting. But this is just an concept, right? We don't have any syntax like this and in our Java or C++. This is for the sake of creating a concept in our minds for us to pick the objective of this course. And then, yeah, second, turn down to lower the setting by 1 degree. And then next is to use default. So we in this function, we can reset the thermostat to a present value. And then fourth is to check current setting to report the current thermostat setting. So as you can see, there's an ADT implementations in there. And then, so to further relate this in our profession as a programmer, here is a mental model offered by a data abstraction gives us an informal understanding of how and when to use it. But because it is simply a mental model, it does not tell us enough information to program with it. In this example, this is a C um, roughly coded and an abstract data type captures in this model and programming language interface. This isn't a particularly good ADT actually, but it illustrates the main point, which with the information provided in here, we can see that this manipulates a data feed set instance as a set of single-digit integer in a set from the data set 0, 1, 2, up to 9, right? Looking into a more general ADT, it includes additional set operations, such as this. It displays an empty functions. So it verifies if the value is empty. So right then and there, the logic could proceed if it validates the truth. Yes, and then given with this design, the operations should always be sufficient and useful. ADTs must have enough operations to build the ADT structures called ADT constructors. An ADT must include enough ADT constructors to build all possible values of the domain. The ADT is called complete if it satisfies the property, like for example, a person's list. A person's list could create an empty list. An insert before, it constructs a new list by inserting a record before cursor. Insert after, it constructs a new list by inserting a record after the cursor. And then delete, it constructs a new list by deleting the record of the cursor. So enough with the geeky code. um, as an example, let's say uh, here are the categories that we could see in the ADT operations. Sorry, hindi ko pala nalipat yung. So we have the ADT constructors initial, and then IO operations, which it is an input output, but it is not always necessary. The type conversion, it sometimes interfaces to existing data types, which are necessary. And then test operations, an ATT must provide enough test operations for the client to check all preconditions of the ATT operations. Assignment copy operations, especially if the data is created on the free store. Selector operations, which access functions. And then the destructor operations, which is especially used when if the data is created on the free store. In here, um, let's see. Here is the next code. I could show you. I don't know if you can see it clearly, but in here there is a function is full, which will always return false, unless if you have a very consistent way to access the information regarding the available dynamic memory. So um, the uniformity with ADT will be followed. So an advice in using ADT is to keep it simple, just to keep it consistent with the intent of the abstraction. So moving into the implementations, we have exhibit here an implementation that compares the abstract assertions versus the implementation assertions. Separate views make correctness more difficult to achieve. The implementer must ensure the agreement between these two perspectives. What the importer sees as the essential initial conditions for function invocation are sufficient to ensure that the implementer believes to be initially true. Second, the operation is correct in the view of implementer. Third is what the implementer guarantees as final conditions are sufficient to ensure that the importer expects to be true afterwards. With here, assertions must be precise and assertions must be understandable. So while we are using these ADTs, of course, we will be make use of these sequences. And naalala ba natin yung ating college days for these notions? So this will be handy for us to be guided into our sequences. So we can see in this example, I have provided in our next slide, the following defines stack ADT using assertions in the sequence notation with a bounded vector implementation. And here, it has described as a list as we can it has is empty, is full, and then that's where can validate the pop with its length and stack. So another implementation of ADT is the ring buffer implementation of a queue. There are many uses of queues in computer systems. It provides simulations, queuing theory, handling fair servicing of multiple requests of a limited resource such as printing, disk access, tsaka yung CPU time natin may improve. So let's move on to the next slide. Here is the abstract functions. Here is an illustration that structure the diagram na pyramid. So you can see at the top, we have the main application program. For example, a spell checker. The code that occurs that this level is very specific to this application and is the main thing that differentiates a spell checker from, let's say, a spreadsheet. On the other hand, at the very bottom of the hierarchy, we have all the basic primitive data types and operations such as the int type, like what we said earlier, the char type, the addition, subtraction, so on, that are provided by this example. we have the C++, the the one that uh, uh, is indicated on the leftmost part. And then in between those, we have all the things that we can build on top of the language primitives on our way working up towards our application program. Just above the language primitives, we have the basic data structures like link, list, or trees. We're going to spend a lot of time of the semester looking into these kinds of structures. Though you may already be familiarized with some of them, they are certainly very important. Yet we stop at this level. We would go wind up. For the very applications, let's stick into this ADT. Um, for most companies and therefore most programmers do not move from one application to a wildly different application to the next project. Programmers who've been working on most accounts receivable are unlikely to start writing compilers in the next week, and programmers who have been writing compilers that are not going to write control software for jet aircraft. Well, di naman nakarelate dito. I don't know, baka meron kayong ganun. Pero on our end, yes, we've been working with accountants kasi so we experience this complexities like what this ADT is imposing, this concept is imposing. Um, like for example, the people who are currently working on the spell checker may be very well be assigned to work on a grammar checker next month, for example, or on the other text processing tool. That means that any special support we design for dealing with text, words, sentences, or other concepts natural to this application may prove valuable in the long run because we can share that work over the course of several projects. So I hope some all of you can relate with that. And so on the top of the basic data structure, we expect to find layers or reusable libraries. Just above the basic data structures, the libraries are likely to provide fairly general purpose structures, such as support for lookup tables, user interfaces, and the like. As we move up to the hierarchy, the libraries become more specialized to the application domain in which we're working. As you can see doon sa mga nabanggit na syntax kanina, just below the application level, we will find support for concepts that are very close to the spell checker, such as words, misspellings, and corrections. So, ganun na siya sa high level natin, na ginagamit like yun nga, Java and C++. The library actually makes up all but the topmost layer of this diagram may contain individual functions or groups of functions organized as abstract data types. Okay. And then more for the abstract functions. A procedural abstraction is a mental model of what we want a subprogram to do, but not how to do it. That's a different topic. For example, if you want to compute the length, tama ba? Pareho tayo nakikita. Yeah. If you want to compute the length of a hypotenuse of a right triangle, you might write something like double hypotenuse, like yung side niya, di ba? I-multiply mo, tapos ipa-plus mo yung side 1 and side 2. Understanding that the function is supposed to compute a square root, and if we have no idea, the square root actually gets computed, right? That's because we understand the square root is. So, that's the same concept nung sequence na kanina natin dinidiscuss. When we start actually writing the code, we implement a procedural abstraction by assigning an appropriately named function to represent a procedural abstraction. In the main code, calling the function, trusting that it will actually do what we want, but not worrying about how it will do it. And finally, writing a function body using an appropriate algorithm to do what we want. So parang di naman hard code, pero isa-isahin mong gagawin yung logic based on your expectations. In practice, there may be many algorithms to achieve the same abstraction. That's true. And we use engineering considerations such as speed, memory, requirements, and ease of implementation to choose among those possibilities. For example, the square root function is probably implemented using a technique completely unrelated to any technique you may have learned in grade school for computing square roots. On many systems, square root doesn't compute a square root at all, but computes a polynomial functions that was chosen as a good approximation in the actual square root, and that can be evaluated much more quickly than the actual square root. And this initial approximation may then be refined by several iterations for a numerical technique known as the I don't know, the Newton-Raphson method, sabi dito sa research. Does it bother you to hear that the implementation of square root might not? Ah, kasi 'di ba kapagka nagko-code tayo, we intend to do or to write what we actually want as a result. But we wouldn't consider kung meron na palang available on a certain library. Pero mas ideal siyempre kung gagawin natin efficiently kung anong meron yung library, lalo na pagka yung ginagalawan natin uh, na program is in object-oriented programming. So it will be much organized if we could use it efficiently. Yeah, correct. So next is a representation invariants. The abstraction function explains how information within the module is viewed abstractly by module clients. However, this is not all we need to know to ensure correctness of the implementation. Consider the size function in each of the two implementations. For example, this list set no dupes. So what does it do? It lists the all unique values. So in this syntax, you would understand what does it do, in which the list of integers have no duplicates. The size is just the length of the list. So let's put it into let size equals to list dot length. But as you can see, for list set dupes, which allows duplicates, we need to be sure not to double the count duplicates element. So we will write it as let rect size equals function, tapos equate it into size plus yung if if ht then 0 as 1. How we know that we don't need to do this check in list set no dupes? Since the code does not explicitly say that there are no duplicates, implementers would not be able to reason locally about whether functions like size are implemented correctly, right? The issue here is that the list no set no dupes representation, not all concrete data items represent abstract data items. That is, the domain of the abstraction function does not include all possible lists. There are some lists such as 1:1, 2 that contain duplicates and must never occur in the representation of the set of list set no dupes implementation. The abstraction function is undefined on such list. We need to include on a second piece of information the representation invariant to determine which concrete data items are valid representations of abstract data items. So if we think about this commutative uh, ito yung code nga na pinakita, we see that there is a crucial property that is necessary to ensure correctness, namely that all concrete operations preserve the representation invariant. If this constraint is broken, functions such as size will not return the correct answer. So we have to be considerate with that. Looking into this diagram, the relationship between the representation invariant and abstraction function is depicted in this figure. We can use the rep variant and abstraction function to judge whether the implementation of a single operation is correct in isolation from the rest of the module. It is correct assuming that the function's predictions hold of the argument values. the concrete representations of the arguments satisfy uh, the rep variant. We can show that all new representation values created satisfy the rep variant and the commutative diagram holds. The invariant makes it easier to write code that is probably correct because it means that we don't have to write code that works for all possible incoming concrete representations, only those that satisfy rep invariant. For example, in the implementation list no set no dupes yung kanina, we do not care what the code does on the list that contains duplicate elements. However, we do need to be concerned that on return we only produce values that satisfy the rep invariant as suggested in this figure. If the rep invariant holds for the input values, then it should hold for the output values, which is why we call it an invariant. Okay, and then next, to add for the representation invariants, an abstract data type is a type equipped with a set of operations for manipulating values of that type. An ADT is implemented to provide by providing a representation type for the values of the ADT and an implementation of the operations defined on values for the representation type. What makes an ADT abstract is that the representation type is hidden from clients of the ADT. Consequently, the operations that may be performed on the value of the ADT are the given ones. This ensures that the representation may be changed without affecting the behavior of the client since representation is hidden from it. The client cannot depend on it. This also facilitates the implementation of efficient data structures by imposing a condition called representation invariant. The representation that is preserved by the operations of the type, each operation that takes a value of the ADT as argument may assume that the representation invariant holds. In compensation, each operation that yields a value of the ADT as result must guarantee that the representation invariant holds of it. If the operations of the ADT preserve the representation invariant, then it must truly be invariant. No other code in the system could possibly disrupt it. Put another way, any violation of the representation invariant may be localized to the implementation of one of the operations. It significantly reduces the time required to find an error in the program. To make these ideas concrete, we will consider the abstract data type of dictionaries. A dictionary is a mapping of keys and values. For simplicity, we take keys to be strings, but it is possible to define a dictionary for any ordered type. The values associated with keys are completely arbitrary. Viewed as an ADT, a dictionary is a type of of dictionaries, mapping strings. In short, data dictionary. Nabanggit din kanina sa subject natin. A simple implementation of a dictionary is a binary search tree. A binary search tree is a binary tree which values of an ordered type that the nodes are arranged in such a way that for every node in the tree, the value that the node is greater than the value of any node in the left child of that node and smaller than the value of any node in the right child. It follows immediately that two nodes in a binary search tree are labeled with the same value. The binary search tree property is an example of a representation invariant on an underlying data structure. The underlying structure is a binary tree with values at the nodes. The representation invariant isolates a set of structures satisfying some additional more stringent conditions. So I hope you can make use of that. Another example is this. We may use a binary search tree to implement the dictionary as follows. So as you can see, notice that empty is defined to be valid binary search tree. That insert yields a binary search tree if its argument is 1, and that lookup relies on its argument being binary search tree. If not, it might fail to find a key that in fact occurs in a tree. The structure binary search key is sealed with the signature DICT to ensure that the representation type is held abstract. So the difficulty with binary search trees is that they may become unbalanced. In particular, if we insert keys in ascending order like this one, uh, if you can see in there, the representation is essentially just a list, right? The left child of each node is empty. The right child is the rest of the dictionary. Consequently, it takes time in the worst case to perform a lookup on a dictionary containing the n elements, correct? Such a tree is said to be unbalanced because the children of the node have widely varying heights, correct? Were it to be the case that the children of every node had roughly equal height, then the lookup would take time a considerable improvement. So can we do this better? Um, mm, mm, mm. Maraming approaches. So we have approaches to be suggested. One that we will be considering here is the instance of what is called the self-adjusting tree. So in our work we call it dynamic. So called a red black tree. The reason of the name will be apparent shortly. The general idea of a self-adjusting tree is that the operations on the tree may cause a reorganization of its structure to ensure that some invariant is maintained. In our case, we will arrange things so that the tree is self-balancing, meaning that the children of any node have roughly the same height. As we have just remarked, this ensures the lookup is efficient. So how would it be achieved? This is by imposing a clever representation invariant in the binary search tree called the red-black tree condition. A red-black tree is a binary search tree in which every node is colored either red or black, with the empty tree being regarded as black, such as the properties it could hold into two conditions which ensure that the red black tree is balanced binary search tree. Here's why. First, observe the red black tree of black height h has at least two uh with exponent at h minus one nodes. We may prove this by induction on the structure of the red black tree. The empty tree has black height 1 since we consider it to be black, correct? And to ensure that logarithmic behavior, all we have to do is to maintain the red black invariant. The empty tree is a red black tree, so the only question is how to perform the insert operation. So first, we insert the entry as usual for a binary search tree with a fresh node starting out colored red. In doing so, we do not disturb the black height condition. We might introduce the red-red violation, a situation in which a red node has a red child. But when we remove the red-red violation, by propagating it upwards towards the root by a constant time. It's a transformation of the tree. One of a several possibilities which this transformation either eliminate the red-red validation outright in logarithmic time. Push validation to the root where it is neatly resolved by recoloring the root black, which preserves the black height invariant. So, moving on with the notions of equality, which is the last topic, magla-lunch na yata kayo. So, as an abstract data type was defined as a set of data values and associated operations that are precisely specified independent for any particular implementation. For these axioms, one may define equality between stacks, define a pop function which returns the top value of a non-empty stack. For instance, the predicate is empty, sub s, may be added to define with the following additional axioms. So every language has mechanisms for comparing values for equality, but it is really the kind of equality you want. So in Java or C++, for instance, the built-in operations equals is used to check for equality. Now, for primitive types of equal behaves like you would expect. That is, one is true and one equals two is false. Similarly, true equals true is true, but true equals false is false. But what happens with objects? What if objects are involved, not numerals? Object 1 equals object 2 is true exactly when two objects are the same actual object. When an object is created, it gets allocated somewhere in memory. Um, we consider two objects by the same actual object if they live at the same address in memory, correct? In other words, equals also checks object identity. So for next slide, you can see an example in here equating the two objects. Although object 1 and object 2 look the same, they are different objects. As for example, I have described earlier. Each invocation of, for example, drawing that empty calls new, which creates a different object every time. Object identity is useful, but it is rarely what we want. In particular, I may want to say that the two drawings are equal if they contain the same sequence. So correct. And then the following principle can be used to help you devise a suitable notion of equality for an ADT for which you've already determined the creators and accessors, and can be paraphrased as follows. If two objects behave the same, such as yield the same observations, no matter the situation, they should be taken to be equal and considered equal. So more formally, we could use the term principle of indistinguishability, wherein if two values, object 1 and object 2, if of an ADT are such that for every uh, successor na, let's say, object n in the ADT, applying object n to object 1 and object 2 with the same arguments yield results that are equal, then we should take object 1 that equals object 2 to be true. If you think about it, the converse also should also be true. If two values are considered equal, then they should yield the same answers to any accessor. So really, equality ought to be determined by the results of invoking accessors on values of the ADT. Um, for every ADT we are going to have an equality operation capturing whatever notion of equality we deem reasonable and useful for values of the ADT. Following the principle of indistinguishability, we are going to call the operation equals. What should be the signature of the equals equation? Of course, certainly equals should take a value to compare the implicit argument to and should return a Boolean value. But what should the type of argument value be? Two choices are usually suggested. Either take the type of the argument to be the type of the ADT or allow any type of argument to be compared with the value of ADT for a variety of reasons, not at least of which being that in Java, that's how you ask you to implement equality. Because equality is so important, Java requires that every class implements an equals method. If one is not given, then a default is provided, correct? For those Java users out there. Then a default is provided. The equals method will just check the object identity equals. Again, generally, not what we want. Suppose we wanted to implement a data structure to represent sets of objects. The main operations you want to perform on sets is adding and removing objects from the set and checking whether the object is in the set. The naive approach is to use a list But of course, checking membership in a list is proportional to the size of the list, making the operation expensive when it sets to become large. So in a growing system, it's not um, advisable. A more efficient implement is to use a hash table actually. A hash table is just an array of some size, number, and each cell in array is a list of objects. To insert an object in a hash table, you convert the object into an integer. That this is what the hash code is used for. Convert the integer into an integer I between 0 and n minus 1, for example, using modular arithmetic, and use I as an index into the array. You attach the object at the beginning of the list, position I to check the membership of an object. You again compute the hash code of the object, turn into an integer I between 0 and n minus 1 using modular arithmetic, and look for the object in the list at index I. Correct? So we're usually using it in a loop. The hope is that the list in each cell of the array are much shorter than overall list of objects would be. But in order for it to work, of course, we need some restrictions on what makes a good hash code. Generally, hash codes are computed from data local to the object. For instance, the value of its fields. In Java, it has a number of methods called canonical methods that requires every class to implement. If you don't implement explicitly one of those canonical methods, the system assumes a default implementation again. Those methods usually are the equals, the hash code, and to string. Yeah, and to wrap this up, uh, as a summary, abstract data types allows the programmer to define a complex data structure and an associated collection of functions operating on that structure in a consistent way. In a way which abstract data types are realized traditionally as modules, and the way abstract data types may be realized using object-oriented programming techniques. Approaches must be regarded as being orthogonal to one another and being to some extent complementary. Uh, this deserve to be integrated on a common framework, on any common framework that we're being designing as a programmer. So I have prepared some questions. I don't know if this is still needed, but this is part of the presentation slide, and that ends my report. Thank you, Doc. Thank you, classmates.
Okay,
Thank you,
so
Doc.
thank you very much. To sum up the discussions of our first presenter, of course, we need to accept the fact that what abstraction means, no? Abstract data types are purely theoretical entities and used among other things. And to simplify the description of abstract algorithms, to classify and evaluate data structures and normally describe the type of system of a programming languages. Now, abstract data types are an instance of a general principle in software engineering, which goes by many names with slightly different shades of meaning. And I will give you some names that are used for this idea. When we say abstraction, we are omitting or hiding low-level details with a simpler or higher-level idea. When it comes to modularity, dividing a system into components or modules, each of which can be designed, implemented, tested, reasoned about, and reused separately from the rest of the system. We have also the term encapsulation, building walls around a module. Actually, this a hard shell or capsule, so that the module is responsible for its own internal behavior, and bugs in other parts of the system can't damage its integrity. We have also information hiding, the hiding details of a module's implementation from the rest of the system so that those details can be changed later without changing the rest of the system. And we have the separation of concerns. This making a feature or concern the responsibility of a single module rather than spreading it across multiple modules. If you are a software engineer, you should know these terms actually because you will run into that frequently. The fundamental purpose of all these ideas is to help achieve the three important properties that, of course, the safety from bugs, ease of understanding, and readiness for change. The abstract data type is characterized by the following properties. Okay, sabi nga kanina ni presenter, it exports a type, it exports a set of operation, and this is called interface. And operations of the interface are the one and only access mechanism to the types of data structures. Now, when it comes to implementation of implementation is carrying out execution or practice of a plan, a method or a design idea, model, specification, standard or policy for doing something. As such, implementation is the action that must follow any preliminary thinking in order for something to actually happen. In system implementation, it is the process actually for defining how the information system should be built or the physical system design, ensuring that the information system is operational and used, ensuring that the information system meets a quality standard. The abstraction in design is the process of removing successive levels of detail from a representation in order to capture only the essential features of a system. If implementation involves a production process, a manufacturing system which uses the established technical and management process may be required. Actually, the purpose of the implementation process is to design and create a system element conforming to the element design properties and or requirements. The main benefit of using an abstract class is that it allows you to group several related classes as siblings because abstractions helps to reduce the complexity of the design and implementation process of a specific program or software. The ADTs are defined by a specification abstract state plus collection of procedural abstraction, not a collection of procedures. Together, this procedural abstraction provides some set of values, all the ways of directly using that set of values, creating, manipulating, and observing. Creators and producers make new values, and mutators change the value, and observers allow one to distinguish different values. Connecting implementation to specification representation invariant, the maps objects to Boolean, of course, indicates if the instance is well-informed, then define the set of valid concrete values. And only values in the valid set make sense as implementation of an abstract value for implementers, debuggers, maintainers of the abstraction. And no object should ever violate the rep invariant. Such an object has no useful meaning, abstraction function, maps objects, abstract value, and what the data structure means as the abstract value, and how data structure is to be interpreted. Only define on objects meeting the rep invariant. So, if, for example, if I am the implementers or the debuggers or the maintainers of the abstraction, each procedure should meet its spec by doing the right thing with the concrete representation implementing a data abstraction. And to implement a data abstraction, we need to select the representation of instances. The rep, in Java, typically instances of some class you define. Implement operation in terms of the rep, choose a representation so that it is possible to implement required operations. And the most frequently used operations are efficient, but which will this be? Abstraction allows the rep to change later. Again, abstract data types are characterized by their operations. So operations can be classified into creators, producers, observers, and mutators. An ADT's specification is a set of operations and their specifications. Take note that a good ADT or abstract data types is simple, it must be coherent, adequate, representation independent, and preserve its own invariants. An invariant is a property that is always true of an ADT object instance for the lifetime of the object. Invariant must be established by creators and producers and preserved by observers and mutators. Representation exposure threatens both representation independence and invariant preservation. Java interfaces help us formalize the idea of an abstract data type as a set of operation that must support, of course, by a type. It must be supported by a type. These ideas connect to our three key important of a good software as follows. No? Ano ba yung three ideas connect to our three key properties? Nandyan yung safe from bugs. No? A good ADT offers a well-defined contract for a data type and preserve its own invariants so that those invariants are less vulnerable to bugs in the ADT clients. And violation of the invariants can be more easily isolated within the implementation of the ADT itself. Another thing is it must be easy to understand because a good ADT hides its implementation behind a set of simple operations. So the programmer using ADT only need to understand the operations, not the details of the implementation. And the last one is ready for change. Representation independence allows the implementation of an abstract data type to change without requiring changes from its clients. And that's it for today. Thank you very much.
Thanks, Doc.
Okay, when it comes to do sa array, it is applicable with web. Yes, of course. Even web applications required to have to use an array. Even a simple JavaScripting, no, we are using an array. Okay. Do you have any question pa so far, class? Before we end this class?
No question, sir. No question.
Doc,
Oh,
wala na pong question.
sige. So what will be the So far okay na. So next meeting, this coming Saturday we don't have class. So next Saturday, so topic number 1 for ASDI and topic number 3 ba tayo for database administration.
Tama po.
Okay. Noted? Okay, sige Sir Dodi, pakisend na sa akin ito para ma-post ko na agad. Hinihingi na ni Ma'am Susan.
Yes po. Pagka-upload po sa Google Drive. Apo. Thank you po.
Okay, thank you very much. See you next meeting. So next meeting we start by, pwede bang 7:30? Kasi parang imagine inabot tayo ng 12.
Sorry po.
Okay po, Doc.
Noted
Okay
po.
po.
Noted.
Sige, 7:30 tayo next meeting ha. Bukod sa Saturday, next Saturday.
Apa.
Okay? For your final project, dahil may bago tayo,
Okay
kindly
po.
assist naman, please. Ha? Salamat. Paki-assist yung mga bago sa project, ha?
Apa.
Okay, thank you very much. God bless everyone.
Thank you po.
Sis Rax,
Po.
di ba sabi mo gusto mo nang mag-meeting sa project? Reset mo na lang siguro ibang
Thank you,
araw kasi
everyone.